The energy required for the aeration system, it's a calculation that's highly dynamic, obviously, given the dynamics of the aeration system, and allows us to then compute how much it costs once we know the power tariff from a power company. So starting from revisiting the alpha factor, remember that the alpha factor is there to scale down the performance from clean water to processed water. We need to maintain the dissolved oxygen level in the water, and to do so, we have to transfer enough oxygen to overcome the oxygen requirements in the green condition over there. The equation is the oxygen transfer rate equals the oxygen feeding rate, which is WO2, times the alpha SOT, the oxygen transfer efficiency in processed water. With time in operation, that's probably going to be better to be alpha SOT. Now, the proportionality is with airflow rate, because 23% of the air is oxygen times the density of air, you get WO2. We turn that around to get the airflow rate, which is what we need in the blower house. That's what we pay for. Remember, the blower power is proportional to the airflow, right? So the airflow rate is proportional to the oxygen we need in the water divided by the efficiency. Now, we said also earlier that the COD changes every hour of the day on the horizontal axis, and therefore the airflow rate changes every hour of the day on the vertical axis. Let's go back and look at the adiabatic equations. On the bottom of the slides here, we have the power equals the mass flow of air, okay, which is W. Earlier we said WO2 is only 23% of it, but this is the full 100% because we have to pay also for the nitrogen we blow, even though it doesn't do anything but mixing. So W times R, the gas constant, T is the inlet pressure, the inlet temperature, 28.97 is the molecular weight of dry air, little n is the specific heat ratio or the adiabatic compression ratio. Call it as you wish. It's n equals k minus 1. K is the specific heat ratio, so Cp over Cv. E is the efficiency of the blower. It depends on the machine, of course. P2 is the discharge pressure. P1 is the inlet pressure. The inlet pressure is about 95% of the atmospheric pressure at the site where the blower is sited. And that composes the equation. Now, that's an equation you find in a textbook. This is the proportionality we want to talk about here. The breaker's power in kilowatt, which is from the previous equation, okay, are proportional to the airflow rate. Once the alpha SOT becomes smaller, either different hour of the day or wet time, because there's a fouling factor F that intervenes, the airflow rate has to be much higher in proportion. So, if we calculate the power, okay, and we divide it by the volume of the water, we get that trend line you see in the top part. It's called power density, it's watt per meter cube, and you see it goes up and down every day, and there is a peak and a minimum, and it's about twofold the variation, thereabouts, every day, which means that this is the economic, the energy reflection of the dynamics of the alpha, and if I have a power bill, then I can extract the tariff from. The tariff is the structure which you pay power. You pay for the power, you pay for the energy, okay? The energy being the integral of the power, you see in the bottom. So the power is how much power you draw instantaneously, and you pay for that service. That's the cost of getting the electrical service. The energy is the consumption, is how much of that power you use in an hour time, okay? So it's the integral, and that will be the watt hour per meter cube, the energy intensity. You pay for both in an industrial power tariff. So integrating these two times the tariff structure over a period of a month, it give you the monthly energy cost. If you only look at the energy consumption in, say, kilowatt hour in a month, it's probably half of your power bill. The other half is the power demand charge, because this is tri-phase, usually medium tension power that requires a lot more, a lot costlier operation in order to supply it, and it costs a lot more on the end of the demand, okay, to rephase it and so on and so forth. So it's not as simple as the household power bill. Now the power input for an aeration system, the way we calculate is we look at how much oxygen is in the water and how much power we draw from the wall, from the wire. So it's wire to water calculation. Now it's very important because in between there are all the parts of equipment, but ultimately what we pay for is at the wall, at the wire. So we want to use wire power, not just the mechanical power of the blower, which is the previous equation. The previous equation tells us the mechanical power of the blower, but there is also the motor and any other electrical unit that are there to condition the power. So we want to use the wire power when we do this normalization overall. And remember that alpha changes, over time, over hour of the day, and over time in operation, because there is a fouling factor. So the OTR will change as a consequence. So we have clean water examples of efficiency. We tend to normalize it per unit submergence of diffusers, not the depth of the tank. The diffuser may be above the floor, right? But it's the depth at which the bubbles are released. So 6 to 7.5% per meter. It's a good number for SOT in clean water. But when you go to wastewater, it's probably half of that. Okay, so 3 to 4% is a number that we should expect per meter. So every meter of that, you get 3 to 4% of the oxygen from the water, from the bubble going to the water. That means that if you have a tank that is 5 meters deep, at best you get what? 20% of the oxygen going out. Oxygen is 21% of that bubble. So at best, you get 20% of 21%, which is roughly 4% of the total bubble being dissolved. The rest of the other 96%, I pay for it, and it just transits through the water and mixes. That's all it does. And I gotta pay for 100%, a full bubble. So it's a very inefficient operation to begin with, because it's made inefficient by the low solubility of oxygen. It is naturally occurring. Now, the power measurements could be the wire power, the brake power, okay, and the power that is actually transferred to the water, okay. So we could have surface aerators. These are the type of aerators we haven't really looked much in detail here, because they typically are used for lagoons or for older installations where there is a motor with a shaft and a mixer that splashes the water up in the air in droplets. Those all the power there, it's transferred to the water for mixing and aeration. And in case of like a blower with the air duct that brings the water down to the diffusers, some of that power may be converted into heat. Okay, and so it's slightly different calculation. And what's the difference between wire power and brake power? Well, the brake power is the mechanical power. You run a blower and then you apply a brake to the shaft until it stops, and that gives you the amount of power that is required to brake it. Okay, so brake horsepower. How many horsepower are required to brake the shaft to go all the way to zero? And so that's the mechanical power. The wire power is how much power we need to draw from the wire, from the electricity line. So the wire power is higher than the brake power, because in between there is the electrical motor. There could be a variable frequency drive or any other transformer or other unit that will consume a little bit of power due to inefficiency. So it's very important to spell out how you measure the power, whether wire, brake, or water power, so you are consistent in your evaluation and your comparison, rather than using one or the other to make somebody look good or look bad. And if you look at electrical motors, modern electrical motors are very efficient. So the error is small, okay? It's probably like 5% error between wire and brake horsepower. But if you have smaller motors, older technology motors, or if you have variable frequency drives which can regulate the frequency of the electricity at the cost of some inefficiency, then you really need to be able to parse out these differences. And when you have a gearbox, so the motor is high speed and you will need to reduce from the motor speed to the speed of the mechanical unit, the gearbox itself will have an inefficiency. It's inevitable because there are moving parts and there is friction. So it's very important to understand also the gearbox effect between the motor RPM and the rotor RPM, whether it's the rotor of a blower or the rotor of a mechanical impeller for surface aeration. And we have different types of blowers, and there's a whole blower taxonomy we could go through. But the important thing to remember is blowers operate by blowing air. They don't compress it, okay? The air compression only occurs if you impose a pressure drop at the discharge of the blower. If you take a blower, you put it on a basement, and you run air in and out of the blower, the pressure inlet and outlet is practically the same, okay? And we are in the same room. But if you take a pipe, you attach it to the discharge and impose a pressure drop by, say, putting that pipe into the water, okay, now there is the hydrostatic pressure. Now the velocity, it's converted into pressure, Bernoulli. So what happens is you give up some of the velocity and you release that energy in form of pressure. So some blowers have the ability to discharge a wide latitude of airflows, okay, but at the expense of pressure. And that will be the case of centrifugal blowers. But then you have blowers that are called positive displacement blowers. Those are the ones with the lobes that engage, and they always check, meaning that the blower, what it does, moving at a higher or lower speed, it increases the frequency at which these packets of fluid, of air, are squeezed through to the lobes and moved forward. But you don't have a very high change in airflow rate because you can overcome variable pressures on the other side because the lobes always check, they prevent backflow. Whereas if you have a centrifugal blower, you always have the risk that if you have too much back pressure on the discharge side, well, it's not a perfect check between the rotor and the casing because otherwise it will touch it. And so at some point you're going to have the blower being unable to overcome the discharge pressure. That condition is called a surge. When the blower surges, you will not be able to move the air forward and the blower shuts down because it starts vibrating and it could effectively destroy the basement of the blower. So blowers that are centrifugal in nature have a propensity to go to surge if there is too much pressure, but they can also be very large. So large plants always use centrifugal blowers. And blowers that need to be used with variable pressure, but not with a big difference in airflow rate, then are used in plants like sequencing batch reactors, perhaps MDRs. Then positive displacement blowers become a much more appealing type of technology. Now, centrifugal blowers can also be tuned in their airflow, not by changing the speed necessarily of the rotor, but by keeping the rotor at fixed speed and changing these little vanes. There are little blades that they can curtail the flow going in and out and regulate the pressure with a control system. And so you have the inlet vanes that are they open like a fan and close, okay? And these little blades can regulate how much air goes into the blower. And the discharge vanes on the other side, or the guide vanes, that what happens is they change the pitch at which the air that goes through the centrifugal volute exits. So they could be along the air streamline, or cut it a little bit, or be in a cross. And so what happens is you can use those instead of using just a regular butterfly valve to really to change the flow and regulate the flow at the discharge point, not just downstream, by creating a pressure drop. So that way you can have a turn up and turn down ability. You don't run them only at fixed speed.